Hello and welcome to Tribe Topper. In this video session, you are going to learn about the kinetic model of an ideal gas. First of all, we'll talk about the key assumptions of the kinetic theory. So I have taken 5 points here and all of these are important. So let's discuss them one by one. That a gas consists of a large number of identical tiny particles called molecules and which are in constant random motion. So generally your gas will consist of very tiny particles and a large number of particles, which of course we call molecules, and these molecules are all the time in constant random motion. That's our first assumption. Second assumption, a very important one, that each molecule has negligible volume when compared with the volume of the gas as a whole. So volume of these molecules are very small. That's why we say negligible as compared to the total volume of the gas as a whole. Negligible as compared to, then we have the molecules, because they are in constant random motion, so they undergo perfectly elastic collision. So they collide but they bounce back with the same velocity, so they don't lose their kinetic energies or momentum. That means in an ideal gas, the molecules undergo perfectly elastic collisions all the times among themselves and also when they collide with the walls of the container. And of course, during collisions, each momentum of each molecule is also reversed. The momentum of each molecule is also reversed. That means if while going it was mv, while coming back it is minus mv. So the total change in momentum that happens is going and coming. So mv minus mv. So that actually leads to a twice of mv as a change and not zero, because the directions are opposite, and when you subtract, the negative sign becomes positive. Now there are no intermolecular forces between the molecules between collisions. So the molecules, when they collide, there are no intermolecular forces in gases, we know, because they are far apart. And if it is an ideal gas, we say absolutely no intermolecular forces. And each molecule produces a force on the walls of the container, which averages out to produce a uniform pressure throughout the gas. Because when molecules are going, I found out here there is a change of 2 mv. So when the molecules go and hit the wall and then come back, there is a change of momentum happening, and this takes a very small interval of time t, and by Newton's second law, which you've learned in mechanics, then rate of change of momentum gives you the force that each molecule is going to exert on the walls of the container, and that force over area gives you the pressure. So these are 5 important assumptions of kinetic theory. You should definitely know these because these can be asked as in paper 1 also as well as paper 2. So you should be able to identify the correct assumptions of kinetic theory. So next we have is ideal gas equation. We have already done one form of it, PV is equal to nRT. But now assuming the kinetic theory of particles, so if this is a cubical box, then just assuming that your particles are going in one direction with a velocity Vx or Cx and then bouncing back with the same velocities, and there is a change in momentum, that rate of change of momentum gives you the force, and that force over unit area gives you the pressure. And then we figure out that this is, suppose Px is pressure for one particle, then along the x-axis you average it out for all the particles along all the directions, and using all that we get another equation for ideal gas, which says that P is equal to 1 by 3 rho c square. So what we have done, we don't really need to know that how you reach this equation, but yes, the basic concept you should know, that we consider one particle motion, that how it goes to the right. So we consider motion of one particle along the x-axis, then it bounces back, it's a perfectly elastic collision. So there is a change in momentum which is 2 mcx. We divide it by the time of interval, you get the momentum in one particular direction. Then you find that out, this is the you get the force acting in one particular direction along the x-axis, and then you need to figure out that this force over the area of that side, knowing the side dimensions, you can find out the pressure and mass of the particles changing into volume, into density. So using all those equations, this is another form of ideal gas equation we have. P is equal to 1 by 3 rho C square. So rho here is the density of the gas and C is the velocity, the average velocity of all particles. So that's the ideal gas equation, another form. P is equal to 1 by 3 rho C square. And for the molecular interpretation of temperature, we continue now that what we just found out above, that pressure is 1 by 3 rho C square. If we convert it into another form where we can replace the density as mass over volume, and for n particles it will be n times m over vc square. And now multiply both sides by 3 by 2, so you get 3 by 2p, and you can take v up, is equal to half nmc square. If you take n outside, you get half mc square. That gives us the kinetic energy. And what is 3 by 2 PV? PV is kBT, because you have done the equation PV is equal to nRT, or it can also be written as kB into T, Boltzmann constant times temperature. So this can be written as 3 by 2 kBT. It is equal to n times half mc squared, that is the kinetic energy. So just assuming it for 1 mole of a gas, n is 1, so kinetic energy is 3 by 2 kBT. So we have used this formula in one of the problems based on gas laws. So kinetic energy is related to the temperature with the relation 3 by 2 kBT. This is another very important expression which relates the kinetic energy with temperature, and this tells you as soon as the temperature increases, the kinetic energy of the particles increases, the number of collisions increase. So this has a lot of applications, and that's all in this video session. In our next video lesson, we are going to talk about the topic 4, that's the simple harmonic motion. Thank you for watching.